Okay, good morning. Welcome to Storage for Renewable Energy Overview, or otherwise known as Energy Storage 101. My name is Kim Crawford. I'm an applications engineer here at Outback Power, and our objective for today is to understand the basics of common renewable energy storage options. It'll take us about 45 minutes, and then we'll open it for questions. And during our Q&A session, our senior applications engineer here, Mark Mays, will be joining us. All right, so let's get started. So what we'll be going over today, we'll go over your basic battery description, then we'll get into some common terms so that we're all on the same page. Then we'll dive into our battery categories with an emphasis on lead acid and lithium-ion technologies, and then we'll get into some frequently asked questions. First, what is a battery? So in its most generic sense, it is a container of two or more cells that are electrically connected, in which chemical energy is converted into electricity and used as a source of power. So if you bear with me for a brief history lesson, the battery has a pretty long history. In 1780, Luigi Galvani, who was an Italian anatomist, used frogs in his experiments, and these frogs were impaled on a brass hook through the spinal cord, which is a little graphic, but then he hung them on an iron trellis in his garden. He would notice every so often that the legs would spastically convulse, and his conclusion was that there was a source of power in the animal itself. However, one of his biggest critics was Alessandro Volta, and Volta should sound pretty familiar to all of us. So he thought that the frog was simply a current meter, and that the source was really the two dissimilar metals, so the brass and iron, being brought into contact. So after he saw that, he used himself as a guinea pig, or a frog in this case, and put two dissimilar metals on his tongue, realized that that was actually the correct assumption, and then he created the voltaic pile. So that's a stack of small discs of zinc, then some brine-soaked cardboard, and silver. He called each of these units a cell. Then he put several of these in series and created the first electric battery. Then, almost 100 years later, in 1859, a French physicist named Gaston Planté invented the lead-acid battery. So batteries have a really long history, and we're just going to cover the basics of what they look like today. Okay, so commonly used battery terms. State of charge and depth of discharge. These two names can be really interchanged. It's mostly, are you a glass half full kind of person, or are you a glass half empty kind of person? State of charge, as we define it, is the quantity of energy remaining in that battery as a percentage. So as you can see on the left, we have our tank of water that we're going to assume is similar to energy stored in a battery, and it's at a 60% state of charge. So there's 60% of that water left. Depth of discharge, on the other hand, is the opposite. It's the quantity of energy we've removed from the battery in percentage form. So on the right-hand side of the screen, you'll see our tank of water, and we've removed 70%, so there's only 30% left. Okay, so energy and power. Energy is a bit of a complicated term. It's not wholly defined in science. It describes the state of a system in relation to the action of forces, and we can only observe it indirectly. So there's no universal energy meter. We observe it through changes in speed, mass, position, those kinds of things. We measure it, if we step back into the metric system for just a few minutes, we measure it in units of joules. But for batteries, we don't use joules. We use either amp hours or watt hours. And we'll get into that in just a second. But first, we need to define power, or the rate of energy transfer. So power can be found by multiplying your current times your voltage. Both of those things we can measure. So power is measured in units of watts. A watt is defined as a joule per second. So here's where we go back to our energy definition. Energy is measured in joules, and then a rate is some quantity over a unit of time. So that's where we get watts, joules per second. And then the second equation you see on your screen is how a watt hour is still a unit of energy. So we have watt hours, and we know that watt is equal to a joule per second, And if we multiply that by hour, there are some constants in here that are not in the equation. This is really just for descriptive purposes. So a joule, so a unit of energy over a period of time times another period of time. That just gives us joules or energy. So that's why we use watt hours and amp hours to measure the energy in our batteries. Capacity. Capacity is also a little bit of a complicated term when it comes to the world of batteries. For lead acid batteries, we measure them in amp hours. So that's similar to a watt hour, but you're not taking into account the voltage of the battery. For lithium batteries, they're generally measured in kilowatt hours. And the next couple of equations you see here, so 200 amp hours, the way you can understand that is if you're discharging your battery at a rate of 10 amps, so that current is a rate, and you have a battery that's rated at 200 amp hour capacity, from 100% state of charge to 0% state of charge is going to be a time period of 20 hours. So divide 200 by 10 and you're left with 20. So for kilowatt hours for lithium batteries, let's say we have a lithium battery that's rated at 2 kilowatt hours. So that equation is our battery voltage multiplied by time multiplied by our discharge current. If we assume that our battery voltage is 50 volts, which is pretty reasonable, pretty common, and we have the same discharge rate, 10 amps, we divide 2,000, so 2,000 watts is equal to 2 kilowatts, right? So 2,000 by 50 times 10. That'll give us 4 hours. So a 2 kilowatt hour battery at a discharge rate of 10 amps will give us 4 hours of power. Capacity ratings. So again, a little bit confusing. So C values are normalized capacities in a specific period of time. They're used to describe current rate without specifying the size of the battery. So if we want to compare a coin cell or a vehicle battery to a large grid size system, then we can use these C values. So 1C is a nominal capacity is just discharged in 1 hour. So if we use that as our baseline, 4C is then the nominal capacity discharged in 1 over 4 or 0.25 hours. So that means that the current is 4 times the 1C current. So if the 1C current was 1 amp, then the 4C current would be 4 amps. And the opposite is true when you're less than 1. So 0.5C, the nominal capacity is discharged in 2 hours, so 1 over 0.5. So that means our current is half of the 1C current. So again, it would be 0.5 amps if we had a 1C current of 1 amp. All right, so now that we're all on the same page with our terms, now we'll dive into our battery types. All batteries are separated into 2 major categories. These categories are primary or non-rechargeable batteries and secondary rechargeable batteries. So your non-rechargeable batteries are alkaline manganese, your carbon zincs. They're basically the batteries that are in your TV remote, your toy cars, things like that. Secondary batteries are where we will be focusing, mostly lead acid and lithium ion. Those are the 2 technologies we're going to go over today. And there are also some other battery chemistries out there. You have nickel-based, flow batteries, liquid metal, brine-based batteries. If we go back to our basic definition of a battery, which is a container of 2 or more cells electrically connected in which chemical energy is converted into electricity, then if you have 2 chemicals, doesn't matter what they are, that produce electricity, that could be considered a battery. But again, we're just going to go over lead acid and lithium ion because those are the most common today in renewable energy storage. All right, so delving a little deeper into the lead acid batteries, your basic construction is a positive electrode, a separator, followed by a negative electrode. The positive electrode is the lead dioxide, the electrolyte is sulfuric acid, and the negative electrode is lead. As you can see here, I have the chemical reaction here at the bottom. I know not a lot of us are chemists, but it is really important to understand this. It's called the double sulfate reaction because both of the electrodes react with the sulfuric acid in the solution. So what happens when those react, they produce what's called lead sulfate. So you can see here on the right side of the equation, PbSO4, that is lead sulfate. Those are crystalline materials that build up on both electrodes, and that creates a resistive layer to electron flow. Since electron flow is limited with this substance on there, you get less power out of your battery. So what we do with flooded lead acid batteries is we intentionally overcharge them, we knock off those crystals, and we have we recuperate all the power that we've lost due to that resistive layer. All right, so now that we have the general construction down, we'll go over the types of lead acid batteries. So as you can see, lead acid batteries are wide and varying. First, we'll start off with the major categories of flooded batteries. So they're called flooded because the electrodes are literally submerged in a liquid electrolyte, so an aqueous solution of water and sulfuric acid. So flooded batteries are further broken down into starting, lighting, and ignition batteries. So those are your car batteries. They have high current for a very short amount of time. Then you have deep cycle batteries, which are what we really use in renewable energy for those kinds of storage. They're able to cycle daily for thousands of cycles, and they're able to do deep discharge. So that's how we get the name deep cycle. Then the last type of flooded battery is a backup battery. So these batteries, they're discharged 1, 2, maybe 3 times a year, and only for a few days. They're usually kept on a float or a trickle charge during the rest of the time period, so when they're not being used, and they just have really long float lives, but if you decided to cycle them on a daily, in a daily application, you would really significantly impact those lives. All right, so moving over to our VRLA batteries, or valve-regulated lead acid batteries, they also break down into 2 other types. So we have gel VRLAs and AGM, or absorbent glass mat VRLAs. So if we go back to our quick history lesson, in 1859, the lead acid battery was invented. So it's one of the oldest types of lead acid batteries. The next major change to that battery was in 1957, so almost 100 years later. And that was when the gel battery was invented by Sonnenschein. They took the liquid electrolyte and added fine silica particles to thicken the electrolyte. So basically they've just suspended the sulfuric acid in almost a jello-like substance. And then 10 years later, again, we had a little bit of change to the lead acid battery. And that was when McClelland and Devitt of the Gates Corporation used an AGM separator, or an absorbent glass mat separator, and they effectively invented the maintenance-free VRLA. So an absorbent glass mat separator is pretty similar to gel. The sulfuric acid is absorbed into that glass mat, and then electrons are allowed to flow through the mat. And these are called maintenance-free batteries because, unlike flooded batteries, where you have to add water periodically because it evaporates during the charge and discharge cycles, VRLA batteries force a recombination of that hydrogen and oxygen into water, so they have a lot less gas production and a lot less water loss. So you never have to add water to these. So overall, lead acid batteries provide the best value for power per kilowatt hour. 97% of lead acid batteries are recyclable. And a lot of these are because they have such a well-supported infrastructure and a lot of research behind it. However, because there's so many types of these lead acid batteries, it's really important to qualify the application. Otherwise, your battery life will suffer pretty significantly. So like I said earlier, your deep cycle batteries, if you decide to use that for, let's say, a backup application, then you're not cycling it very often, and they want to be cycled, you could really impact your battery life. And the same goes for using a backup battery in a daily cycling application. So it's really important to qualify the application. All right, so lead acid types. We'll delve a little deeper into the details here. Flooded batteries. They have a really high cycle life, so most of them are over 1,000 cycles at 50% depth of discharge. So again, that means we're removing half of the available capacity of that battery. They do require the addition of distilled water periodically. They do require ventilation, and these two kind of go hand in hand. So flooded batteries, they produce a lot of gas. Hydrogen is produced at the negative plate, and oxygen is produced at the positive plate. So that's, again, I'm delving a little bit into the chemistry here, but it is important to understand. So hydrogen and oxygen come from the electrolysis of water. So we're taking water and we're separating it into its component parts. So once they are in their component parts, they go from the liquid phase to the gas phase. So you're evaporating that water out of the battery. That's why you have to add water periodically, liquid water, obviously, and you have to ventilate the space adequately so you're removing all that explosive gas of the hydrogen and oxygen. So again, those kind of go hand in hand. Flooded batteries are really tolerant of overcharging. In fact, we do it on purpose when we do an equalization charge to knock all those lead sulfate crystals off. And then a lot because these batteries are so well researched that they're the lowest cost today of any of the renewable energy batteries. And as a fun fact, if you thought the electric car was a new technology, you might want to think again. So in 1899, before AGM, before gel, Camille Janazzi reached a speed record of 109 kilometers per hour. So that's about 68 miles per hour, way back in 1899, with a cigar-shaped electric car powered by a flooded lead acid battery. So you can use that on your trivia nights. All right, so now we'll jump into gel and AGM. Again, that gel is created by adding a fine silica to the electrolyte, and absorbent glass mat, or AGM batteries, they have a similar construction. The electrolyte is absorbed into that glass mat, but they use a highly concentrated acid. So it's 40 weight percent by about 35 weight percent, which doesn't sound like a whole lot, but it actually is pretty significant. So these batteries are sealed with a one-way pressure relief valve. And again, that's because they utilize what's called the oxygen cycle. So they're producing a lot less gas than flooded batteries. This oxygen cycle forces the recombination of oxygen and hydrogen at the negative electrode, which again is reducing that water loss in the gas production. So kind of going along with that, these batteries are what we call maintenance free. We don't have to add water. They have an improved float life. So several of these, they have, I should correct myself. Certain batteries, certain gels in AGM are made for backup applications. Those batteries have improved float lives, and a lot of them are greater than a decade. They have pretty long float lives. However, you do pay for these advantages. They are a little bit higher cost than flooded batteries. So lead acid battery construction. As you can see here, we have BRLA batteries, flooded batteries, and flat plate versus tubular plate. It's a little bit in depth for this particular webinar, but good to note that they do exist. And something that really helped me when I was doing my research for this webinar was the first commercial design of an AGM. I read about it in one of my references. It was stacking of single strips of positive plate, AGM separator, and the negative plate, then rolling it up like a jelly roll. That particular phrase caught me off guard and really helped me envision what the inside of a battery looks like. So hopefully it helps you too. So now we've gone over most of the technology from lead acid of a very high level view. Here you can see that we've listed them all out. We've listed a couple of different characteristics for each chemistry or construction. But overall, the advantages of lead acid batteries, they have a pretty high cycle life. They have fairly low maintenance. Flooded does have some, but it's not too bad. They're 97% recyclable. They have a lower upfront cost, and they have a really well-supported infrastructure. Disadvantages, they are comprised of hazardous chemicals, so that sulfuric acid, especially with the flooded batteries, they're much easier to spill. If you do spill the sulfuric acid, you need to know the appropriate precautions to take. You need to have the material safety data sheet on hand. You need to have all the right personal protective equipment to deal with that chemical. It is very corrosive and very caustic. So also with lead acid batteries, lead being one of the heaviest elements in the world, these batteries are very heavy. They're hard to move around. It takes a little bit of willpower to move one from point A to point B. And then lastly, with lead acid batteries, the capacity of the battery itself is significantly impacted by the discharge rate or the current which you're drawing out of that battery, which is not necessarily true with other chemistries. All right, so now we'll move on to lithium-ion. It was first commercialized in '91 by Sony, so it's a relatively new technology that's still in its development stage. There's not as much research, obviously, as lead acid, but it's still a really popular topic. So metallic lithium is really volatile and unstable, especially when you apply electrical current. So therefore, battery researchers rather, decided to use non-metallic lithium, and that would allow for safer construction of the battery. So that's why you don't see lithium itself with just a battery. You always see lithium-ion batteries. So the positive electrode consists of a metal oxide, and the negative electrode usually consists of carbon. But due to the chemical properties of lithium-ion, all of these batteries need what's called a battery management system. It's a system that really just protects the battery from either overcharging, undercharging sometimes, or a thermal runaway event. So thermal runaway event, it exists with all the chemistries. And just to define what that really means, it's a feedback cycle in which a rapid, uncontrolled release of heat causes even more heat. So heat produces heat, until the process ends with a negative result, such as a system failure or an explosion. Such a condition in a battery in which the elevated temperature destroys the battery. Usually it's caused by the passage of increasing current as the temperature rises. So if any of you can remember the Samsung Note 3s or the Boeing Dreamliner, those were thermal runaway events, and obviously they caused a lot of problems. And then also with lithium-ion batteries, they have a really high upfront cost. All right, so now we'll dive a little deeper into the common chemistries for lithium. There are 6: lithium cobalt oxide, manganese oxide, nickel manganese cobalt oxide, that one's a mouthful. It's otherwise known as NMC, iron phosphate, nickel cobalt aluminum oxide, and lithium titanate. So the interesting thing about lithium titanate, again, when I was doing my research for this webinar, I ran across a paper that used a lithium iron phosphate electrode and a lithium titanate electrode. So the lithium iron phosphate was the negative and the titanate was the positive electrode. It produced some pretty interesting results. So what do all these chemistries have in common? Well, any capacity that is self-discharged can be recovered by a full charge. So self-discharge is that phenomenon in batteries in which internal chemical reactions reduce the stored charge of the battery without any connection between the electrodes. So your battery's sitting on a shelf and it's discharging. It might be minuscule, but it is discharging. So with lithium batteries, you can recover all of that capacity by one full charge. So all of these chemistries also have an extremely high cycle life. Many of the spec sheets that I've seen are in the 8 to 10,000 range, sometimes more. So 8,000 cycles as compared to a lead acid battery, which is over 1,000. And they can also discharge up to 100% of their capacity without permanently damaging the battery. So with lead acid batteries, usually if you go below 80% depth of discharge, then you're running the risk of permanently damaging that battery. But with lithium, you can actually go all the way to 100% capacity or depth of discharge without damaging the battery. However, a lot of battery manufacturers recommend only going to 80 just to extend the lifetime. And the really cool thing about lithium is that they have what's called a flat voltage profile. So again, when I mentioned the lead acid batteries, then they're really affected by their discharge current. Well, lithium is not. So you can discharge at a rate of 10 amps and get 3.5 kilowatt hours out of the battery, or you can discharge at 50 amps and still get 3.5 kilowatt hours out of that battery. There are some operating limits, but they're pretty wide operating limits. Parts of a lithium-ion battery. So again, this is a little bit more in detail than we want to go for this overview, but just know that there are different ways to package lithium batteries, and they have slightly different characteristics. Okay, so technology overview. Again, you can see here all the different chemistries that were listed in the beginning. They all have slightly different characteristics, but overall, the advantages of a lithium-ion battery, they have a really long cycle life. Like I said, 8 to 10,000 or more cycles. They have a set capacity, so discharge current does not affect their capacity. And they are slightly less maintenance because you don't have to add water. However, they do have really specific charge parameters. So depends on your definition of maintenance. You don't have to add water, but you have to be really careful how you charge them since they're not tolerant to overcharging whatsoever. They also do run the possibility of having a thermal runaway event and causing cell failure. It doesn't, so they all run that possibility, although the safest chemistry is iron phosphate, where that potential is very small compared to the others. And then also with specific to the lithium cobalt oxide, cobalt is really hard to find in nature. The abundance is pretty small, so the raw materials are hard to come by, and that will probably increase the cost, and then they'll run out sooner. All right, so now we've gone over our major types that we use in renewable energy and move on to frequently asked questions. So a lot of these come from tech support, things we get asked pretty commonly. How should I prepare a new battery for use? Well, the answer to most of these is going to be consult your battery manufacturer or your manual for specific parameters, but generally, you just have to do a commissioning charge. And again, those parameters are going to be in your battery manufacturer's manual. Can you damage a battery with incorrect use? Yes. Hopefully I've impressed that upon you in the last half hour. It is really hard on a battery, especially lead acid, to go to really low state of charge. Lithium you can, but again, it's usually recommended that you only go to 80%. And do you need to apply a full charge all the time? Lead acid, this column says yes, partial charge causes sulfation of the plates. That's true for most batteries. There are certain kinds of lead acid batteries. So for instance, the Outback 200 nanocarbon, so NC batteries, that do operate fairly well at a partial state of charge. And then for lithium, obviously partial charge is fine. Can you disrupt a charge cycle? So this one is somewhat related to the previous question. the first question was more a long-term state, and the second question is a short-term state. So the answer is kind of the same. It depends on your specific battery chemistry, but more or less it's fine. Should you use up all the battery energy before charging? Lead acid, absolutely not. If you go to 100% depth of discharge, you will permanently damage that battery and it will need to be replaced. Lithium, you can go to 100%, and again, consult your manufacturer specs. So this one's a little odd. Do I have to worry about memory effect? It's almost not relevant to our conversation. The memory effect only affects specific nickel-cadmium batteries. And just to refresh everybody's memory, it's an apparent symptom that the battery remembers the point in its charge cycle where charging began and during subsequent use suffers a sudden drop in voltage at that point, as if the battery had been discharged. So again, it only applies to specific nickel-cadmium batteries, and they're not the batteries that we use with renewable energy storage. So if somebody asks you about it, tell them it's not relevant. And must you remove the battery when fully charged? So lead acid, you need the correct voltage, and it's dependent on the charger. Lithium, charger should turn off. It's not necessary. So that one again is a little bit of an odd question. Okay, so now we've reached the end of our slideshow. References, as you can see here. If you really want to learn more about lead acid batteries and their construction and even some of their history, I would really suggest the third reference by Dr. Pavlov, not Pavlov's bell, not that doctor. He was actually a battery chemist, really smart. The book is easy to understand and has a lot of good information. And finally, if you want to learn more about our batteries and their use in Outback systems, consider taking one of our certificate training programs. You can also earn NABCET credits at the same time. It's a really intensive 4-day class where you will learn so much about our Outback systems. You'll be able to commission and decommission systems, see the products, and there's 2 locations that you can do this. You can come here to Arlington, Washington, or you can go down to Phoenix, Arizona. All right, so now we'll open it up for questions. Okay. So the first question I see is, will this be available on YouTube afterwards? Yes, it will. I'm not 100% sure on the timeline, but it should be close. Oh. Sorry, I didn't see these. Increase the volume. Okay, so it looks like everybody just asked if it was going to be available later, and it will be. Okay, do you have a forum where I could get technical help with batteries and others? We do have an Outback forum. You can find that link on our website, and you can also call technical support at 360-618-4363 if you need to. So the next question, any issues charging lithium batteries with VFX series inverters?
Hi, this is Mark Mays here. Yes, we have what we call advanced battery charge settings in our inverters that are helpful in charging lithium-ion batteries. Most of the batteries, or pretty much all the batteries, require a constant voltage, unlike lead acid that go through a multi-stage charging algorithm. So you can set our absorb voltage, for example, to a constant voltage, and then you can also disable the float. So you can just disable float and stay within a constant absorb voltage. Now, the other thing that some lithium-ion battery charger, the BMS, the battery management system, needs to tell the charger to turn off. We do have that capability through our SunSpec Modbus gateway, which is comes inside our Mate 3 system controller or our access port. There's also some other batteries like the Simplify battery, and I think there's one or two other brands as well that work like a lead acid. In other words, they will shut off automatically if they reach an overcharge situation. There's also an application note on our website about how to set up a Simplify battery, and some of those things that apply to Simplify would also apply to other lithium-ion chemistry. So you can review that, but the main thing is if the BMS needs to tell our charger to turn off, you're going to have to do that with Modbus communication.
Sorry for the quick break. Okay, so we'll start back up. Can I make the certificate training program online? No, it's still in person. Again, it's at Arlington, Washington, or in Phoenix, Arizona. And then will nickel ion be damaged by one-off 100% discharge?
I'd say really that depends on the battery manufacturer. That's really a question for the battery manufacturer. You know, there's so many different chemistries out there. There's no way we could, you know, answer that question with certainty. So if you have a particular battery manufacturer chemistry in mind, I would direct that question back to the battery manufacturer.
And will there be subsequent forums? I'm not really sure what that question is asking. There is a forum on the website. As I said earlier, you can find that link there. If you have a further question, feel free to type it in. And how do you rate the Tesla Powerwall battery? Well, we haven't done any research with that battery yet, so I'm sorry, I can't answer that one either. And the handout does seem to only have initial definitions. That's true. It's a supplemental informational handout. These slides will be available on the Outback YouTube channel shortly. Do you have specific lithium batteries that you recommend? We don't recommend anything specific. However, we have seen a lot of successful installations with the Simplify batteries since they are a drop-in and they act like lead acid batteries. And we also have an app note on our website for compatibility with the Simplify.
So there's a question here that says, should they be equalized? There is no real equalization that's necessary with the lithium ion. I can't imagine unless specifically you know, instructed by the battery manufacturer in general that they don't need to be equalized.
Okay, so I'm going to skip a couple of these questions because it seems like they might be repeats. Do we support lithium? We've been talking about that, and do we have a preferred technology? Do we have or are we planning certificate training programs in the EU? Not at this time, unfortunately. Specific brands, I'm not sure what that was related to. Maybe the lithium question, I think, and I think we already covered that. So is it safe to store batteries under the subfloor of a habitable living area, living space, excuse me?
So basically the answer to that is as long as it meets the environmental specifications of the battery. That's really the simple answer there. If it meets the environmental specifications of the battery, it matches your space, then that's okay. There's the only concern is not really from off-gassing, but thermal runaway. And some lithium-ion battery types are more prone to thermal runaway. The other thing, like for example, the Powerwall is a 400 volt battery, and there are NEC code requirements when installing that battery.
Okay, so the URL for the app note on lithium, that can be found under our website application notes. If you just go to the website, resources, application notes is right there, and it's at that location. Next one, do the Outback inverters charge the OPZV batteries to specification as in their required charging procedures? I'm not necessarily sure what this question is asking, but if you follow the OPZV battery manual and you use the specific inverter manual for setting up your inverter, then they should work together quite well. They're made to work together. Are there inverter hybrids? Again, I'm sorry, I'm not really sure what you're trying to ask here. If you want to clarify a little, that would be helpful. How often should flooded lead acid batteries be equalized in an off-grid application? That's another one of those questions for your battery manufacturer. They do typically recommend a setting, and that could usually be found in the manual. What is the lifeline in any battery, chemical or the plate material? Not sure if you mean lifetime. That is dependent on, again, it depends on your specific battery and your application for that. As I said, you can really cut the life in half of a battery if you use it incorrectly. Can you talk a bit about the batteries available from Outback? Well, that's a really good question. So we're actually going to be holding another webinar next week about what batteries are available from Outback and their specific applications.
Yeah, we're also, the batteries are available on our website. There's also an application note where we talk about how to set up charging for Outback batteries. And that has some background information on the different batteries available from Outback and how to set them up for charging. And again, there's information available on our website as well.
Another question about our certificate training program. So on your screen, you should still be able to see the reserve a space section, and that should have the contact information. And then Mark is also going to talk about that a little bit.
Yeah, so you can just go up to the website, or you can just email training@outbackpower.com. And also there's a schedule up on our website for the certificate training program. And you can go right there and you can see which classes are here in Arlington and which are in Phoenix. I think they alternate 1 month in Arlington and the next month in Phoenix.
Okay, so this next question seems pretty specific, so we're gonna skip that one. So we don't talk to just one person. We want to talk to the whole class. If you do still have a specific question, feel free to contact us at tech support. Does the Outback inverter work with all lithium-ion technologies?
Does it work with all lithium-ion technologies? So we have our advanced battery charging, okay? So if the range of voltage and if the constant voltage requirement satisfies the manufacturer's charging specifications, we are compatible. We can't possibly give a blanket, yes, we support all lithium-ion technologies because we don't know what all those requirements are. And again, I think I mentioned earlier, the main requirement that lithium-ion batteries have is to be able to tell the charging source to stop charging, okay? And there's a few like the Simplify, and there's a couple others that are like the Simplify that have their own built-in protection. They don't need to tell the charging source to stop. They stop already. Now, that said, again, in the Simplify application note, we discuss a method where you can use charge termination control to sense when the current goes down, and then you can disconnect, you can stop the charging that way using charge termination control. So anyway, this is all discussed in the application note, and I think if you read through that, you'll get a better sense of what we're capable of doing.
All right, so the next question, which battery type does the FlexMax charge controller best suited for? I think we've kind of answered that question with the previous answers. What is the next date and time for the next webinar? The next webinar is not set in stone yet, but it will most likely be held next week on Wednesday at 10 a.m. Don't quote me on that. Check the website for the most up-to-date details. Is there a limit to the amount of battery capacity that can be connected to a Radian 8000? I'm assuming you mean an 8048.
So on the Radian, you can put as much battery capacity as you like. We're only going to be able to, invert, up to 8,000 watts. The main thing you need to be concerned about if you're adding a large amount of battery capacity is how you're going to replace that energy. Because the charger on the Radian is a maximum of 5,000 watt charger. So you would, let's say if you're going to have a single Radian and a large battery bank behind it, that you should have additional charging resources like PV array and some other DC charging source to supplement what the Radian can do.
All right, so that looks like all of our questions. So we will go ahead and sign off and hopefully see you next time. Bye.